My name is Rick Branson. I'm a software engineer at Instagram. I work on the backend engineering team. So we basically do databases, caches. We do the sort of product layer on top. We sort of build everything that when it leaves the phone, kind of everything else outside the phone. So I'm here to talk about kind of the changes that we've made in how we use Cassandra since the last time I talked here at the summit in 2013. So just to kind of give you a quick recap, basically where we were was we were moving a bunch of stuff from REDIS to Cassandra. We were saving money. We were getting better availability. It was easier to scale. We had some problems, but we worked through those things. And so here I am today to talk to you about kind of what's new. Give you an overview of what I'm going to talk about. The first section of this, a lot of people ask me about this all the time. I hear you talk about problems with Redis. What exactly is that? And I kind of want to give some more details today as to exactly what that is. I'm going to talk about a whole new category of functionality that we built on top of Cassandra. And I also want to include some useful consumer advice for the people out there using Cassandra in production. So let's get started. What is the trouble with Redis? Well, we moved a bunch of stuff from Redis to Cassandra and some other stuff. We were a huge Redis user. We still have some Redis in production. We're trying to get off of it, all that kind of stuff. So first, I want to talk about the good parts. So what are the things in Redis that it does really well and it's particularly good at, and the reasons why people are attracted to it? Well, it's basically a networked heap. This is why people love Memcache, because you just connect to it, you can talk to it, you have very basic data structures, it's intuitive. It's also got a great text-based protocol, just like Memcache. It's absurdly efficient. It does a ton of work with a tiny amount of CPU. On modern hardware, Redis can crank out something like 150,000 operations per second, kind of out of a single core, and that's kind of without missing a beat. I'm sure it's even higher now on even more modern hardware. It's also really stable. Redis is just it's really, when you upgrade Redis, it doesn't break. It's very reliable. I don't know exactly what it does that makes it so stable, but we've had a really good experience with the quality, the software quality of Redis itself, and it kind of like sets the bar in this sort of very large sort of NoSQL space that has a bunch of different things that it covers. It's also got a couple of these really useful rich types, and not just hashes and lists and the things that we're used to with using Redis, but it's also got some stuff that a lot of other systems really don't have in a way that's really accessible in production. Sorted sets, bitmaps, it's got this hyperlog thing where you can do unique counting efficiently. You won't find very many things that do that across the network very well. If anybody has a better open source solution for sorted sets, I'd love to hear that. Other than just sticking it in memory in a Java heap or something. So what is kind of the darker side? What do I talk about when I say the problems that I've seen people have in production with Redis? I think the first thing that comes to mind for me is you don't know what's in there, and this is a problem with Memcache as well. It's a big flat namespace. It has these like DB things where you can separate things out, but it's not very intuitive. They added, it used to be before 2.8, you basically didn't know what was in there. They added a scan command in 2.8 that let you sort of scan across everything. But you have to enumerate all that, you have to build infrastructure around that, whereas a lot of other systems give you, just a relational database will give you a table, and you have a lot of metrics about those tables. Cassandra gives you column families. So, namespaces in Redis would make a huge difference here. I would love to be able to say, okay, this type of data, you only can use 10 gigs of RAM. That would be amazing, and would make things a lot easier to run in production. The other one that's really big is the snapshot process. So Redis, in order to save its contents in memory, it actually does a fork, and it tries to stream all this data that it has into disk. And what the fork does is it means it creates a frozen snapshot of the process's memory. It's kind of a cool trick you can do on these modern operating systems. But the problem is that it's kind of a race between how fast your data is being updated in memory and how quickly you can stream all that stuff to disk. And you think, oh, it's only about 10, 20 gigs of data. It actually takes quite a while to get that stuff out. So while updates are coming in, all those updates are increasing the amount of memory usage you have. while that stuff's going to disk. So eventually you can get a condition where you run out of memory, and you crash or the snapshot fails. So you can really only use about half, to avoid this condition, you can really only use about half the memory on your machine to safely avoid the condition of this sort of out-of-memory problem. The other thing that's really even more insidious about this is that when you can't snapshot, the instance, your Redis is running and accepting writes. So it's accepting all this data, but you can't save it to disk anywhere. And you're like losing data in production, and that's never fun. The sort of alternative persistence mode, append-only files, where it just sort of writes this log file out, it still has to periodically go rewrite this log file. So that's also a snapshot. So you can't just get out of it with that. It's also single-threaded. And I think we've kind of gone beyond the Chicken Little stage with multi-threaded concurrent programming. Cores are really actually not getting faster. I used to look at, 5 years ago, people would say it, but now it's actually, you actually look at the performance you're getting per core, and it's just not getting any better. And the thing is Redis is just single-threaded, so it can't take advantage of multiple cores. The answer they supposedly say is sharding, but you give away a lot of the advantages. So that means running multiple Redis instances on the same machines that are completely unconnected. The problem is that, like, for instance, if you try to do a set intersection, you have to then do the set intersection across multiple processes and pull all that data into another process. It's all the problems of a distributed database that you typically have, but you get no help with it. It would be really nice to be able to exploit the full power of a machine without running out. The memory allocator, and this is what makes Redis not super great as a cache. And Memcache uses a slab allocator. I'm not going to get into the details of what a slab allocator is, but the other side of that is that Redis uses a heap allocator. And the heap allocator suffers from fragmentation. Anybody who runs Java apps in production kind of understands what heap fragmentation is and how bad it is. You have that problem in Redis. Memcache and this is why Memcache is just a much better cache. It's just more efficient. It uses memory more efficiently. Obviously, it doesn't have all those fancy operations. But we've found that running Memcache in production and learning to live with it and dealing with sort of simpler data structures has been just a better solution going forward. And this could be improved. Facebook has a graph edge cache that uses a slab allocator for basically sorted set data. So it's not impossible. It's also not durable, at least not in the ACID sense. The snapshots basically dump the data out from Redis every few seconds, usually like 60, 120, 5 minutes. That's not really durable. There's this append-only file, like I said earlier. The problem with that is that if you use it in a mode where it's truly durable, where you actually are f-syncing to make sure your data is on disk, it becomes almost unusable in terms of performance. This is something that's been solved for many years in academia, in practice. This is like pretty much everybody else has nipped this problem in the bud. So it's not something that's not fixable. The other thing is that it has unsafe replication. So if you've read up on Kyle Kingsbury's Jepsen project, he kind of details this in the very sort of most detailed way possible in typical Kyle Kingsbury style. The problem I'm just going to highlight here is that Redis basically just is a stream of operations. It doesn't have any notion of from one operation going to the next. So what this actually can be is that there's very little safety around which nodes are replicating from other nodes. If you connect one node to another node, there's no checks that say, okay, is this node in the future? Is it in the past? Is this even the right node to connect to? When you set that replication stream up, it basically disregards everything it has in memory and moves on, which is no fun. If you look at something like Postgres or MySQL, that transaction has to be completely ordered. It will reject, it will resist those kinds of errors, which is very, very helpful in real production situations. Cassandra, when you do ring movement, when you add nodes and you delete nodes and data moves around, it doesn't delete that data automatically for you. You actually have to go say, okay, now go clean up the data. This is a good practice because it means that you don't end up accidentally deleting things. But even more sort of problematic is sort of this some deep-rooted issues that we see, and it really kind of applies to anything that's sort of Redis shaped. There's other things that look like Redis. You may be familiar with things like Terracotta, any sort of persistent in-memory cache. And it's kind of this problem where you don't really know whether, is it a database or is it a cache? It's kind of in between. And it's weird because really, it's all about, can you really lose this data or not? A cache, totally ephemeral. You can lose any key at any time. That doesn't mean that you necessarily you want to lose all your data. You can lose a small percentage of it, and that's because the cache works with an LRU and all the things you're used to with the cache. It's faster, et cetera. A database is an emergency if you lose any data in it. That's what I see as the difference. And when you look at the internals of Redis, it looks like a cache. When you look at the persistence model, when you look at the way that the sort of everything fits together internally, and kind of the operations that are available, it looks like a cache. But it can store data, so people use it that way, just because they can. So the other thing is this memory cliff. Now, again, this happens with anything that sort of has a memory limit. Nobody in the Redis community is telling you it can store more data than you have in memory. There's a little thing there, though, behind that I think a lot of people don't necessarily see. They think in their head, oh, I'm never going to write that, use all that memory. I'm going to control myself. But the problem is that in real life, that's just really smart people do really stupid things under pressure, and they make mistakes. And you want to protect yourself against those mistakes. And what Redis does is you can consume, in really any sort of in-memory system, you can consume all your memory way before any of your alarms can trigger. You can consume 100 gigs of memory in Redis in like 10 seconds. And which is awesome. It's very fast. That's great. But basically, like, it's interesting because it's like because it's faster, it's worse. Which is weird. But this is like why I'm sort of making this sort of argument for this. If you look at Postgres or you look at MySQL or Cassandra or really any other sort of disk-based system, you're going to probably get an alarm. Everything else will probably break before you get to the point where you're in this sort of unrecoverable, I ran out of memory, I can't snapshot, I'm losing data kind of scenario. It's also, it's kind of a trap in a lot of ways. It's a little bit of a developer trap. It looks like a heap. It's got all these awesome, cool, fancy data structures that are just really useful. So it's like the problem is that it hides the serious consideration necessary when you're persisting data. And this is a point that I really want to highlight. Storing data is like creating an API. Once you put that data out in the wild, and once that's in production, you have to support that going forward. You're stuck. You either have to like move everything over to the new format or way that you're storing things, or you have to just live with it. And most people in the real world they live with it. So it's really easy to get yourself into a hole that you can't get out of, or it's very difficult to get out of. With a regular heap or a cache, you just sort of restart it. You roll your cache keys. There's all kinds of stuff. So you have to be very careful with your persistence decisions. Whereas with a cache or like a sort of ephemeral heap, you can sort of really quickly move on from any problems you may cause. And I've just seen a very high sort of what I'm calling a comorbidity rate between bad developer decisions and the use of these types of tools, these in-memory stores. So the most unfortunate part about this is it's kind of unlikely to change, just sort of the attitude of the community around Redis. Multi-threading, data durability, safe replication, really increased memory efficiency. All this stuff is achievable with well-known off-the-shelf designs, been around for decades, academia in practice, and it's just not going to probably happen. A lot of it is around like this sort of no dependencies dogma. It's a sort of very dogmatic mentality. The thing is, though, is that can really happen to any open source project. So really kind of, as a community, we kind of always have to check ourselves and say, what are the things that we hold on to so dearly that are holding us back? What are our blind spots? And I think this is particularly one of Redis's. So we moved out. This is actually a picture of me moving across the country. So the end of last year, we basically decided we were sort of going to move completely off of Redis.
What are you talking about?
We want to be moved out by the end of the year. We think we're pretty sure we will be. We've moved out to a combination of Zookeeper, Cassandra, and Memcache. And you might be asking, Zookeeper, how does this fit in? This is the Cassandra Summit. What are you talking about? Everybody's been dissing it. So we were already using Zookeeper for some service discovery, and it had worked really well for us in production. So we decided to build this system called Zozo. So this is a really weird, like this isn't something that you can just like market. There's never going to be a DataStax of this Zozo-like thing. I'm not even going to open source it because it's probably useless to most of the world. Probably not to actually a lot of people in this room, so this is why I'm going to talk about it. So this means very few writes, and what I mean by that is like less than 1 minute on average, 1 a minute on average for each key. That's not very many writes. That's, Cassandra can do like 100,000 per second or something, so it's like tiny percentage of writes. It basically just stores arbitrary blob keys. They're a few megabytes at most. In practice, it is arbitrary, but in practice we use most of this stuff that's stored in there as JSON. So what does this kind of look like? Well, we have the cloud Zookeeper ensemble over there. Anybody that needs to write, we'll send an update to the Zookeeper ensemble. And then we have, on every machine in production, we have all these agents that run, that pull data down, that watch all of this data. And all the data propagates throughout the whole system in less than a second. And all the agent does is it takes this data and writes it to disk. So it's really, really simple. It just literally mirrors data that's in Zookeeper onto disk. And then all of the processes that we run in production, our application, just read that data off disk. It's really, really simple. The reason we needed this is because the Zookeeper ensemble doesn't really scale past about 10,000 connections. Probably really not past about 5,000 connections, you're pushing your luck. Especially when those connections will, every time you do a deployment, they all cycle, all that kind of stuff. We have a lot of processes that run in production. Our main app is based on Python. So every process needs to connect to the ensemble. It doesn't scale well. There's a lot of churn. So this solves a ton of scaling problems that we had by just running this agent and dumping the data to disk. Certainly possible with Redis, but we were kind of already on this track. This has been really reliable. The watch feature is particularly useful. So what's the type of stuff that we have in here? We have this live configuration thing called knobs, which are just keys with arbitrary integer values. And that allows us to like turn things up and turn things down and like throw flags and all that kind of stuff. We have these sort of small sets of users. So there are people that are included in like feature whitelists and all that kind of stuff. Those are usually under around 250,000 users. We also have like security data sets, like which IPs we want to block right now. That's in the system as well. And this is just sort of the tip of the iceberg. Really any data that fits with this sort of really skewed read and write ratio pattern. Now, some of you may have follow me on Twitter or know kind of my opinion of JSON. You may have seen this coming. JSON's really just kind of a wild, wild west. I know that we're adding it now to Cassandra. The problem is that it's not schematized. There's no validation. People make tons of mistakes with JSON. JSON also has a high comorbidity rate with developer mistakes in the code that I've seen. I think JSON is not necessarily bad, just like I don't think Redis is necessarily bad. I just think you have to understand kind of what its limitations are and where it's appropriate. So, how do we fix this? And this is something that we're working on now. The idea that we have right now is to actually store the data in Postgres and then sort of mirror it out into this sort of more high availability read system. And I'll probably highlight this in a blog post or something like that. So in short, the agent's really simple, doesn't need updating. That's really, really important. Updating that agent means breaking things. You will always break things when you have to update it, at least once, maybe twice, maybe every time. We haven't rolled an agent change. I can't even remember. It's been at least 6 months. So this thing's just been sitting in production, humming along for that long. It just blindly dumps those files to disk. We moved all the smarts sort of into the consumer. So like our app, which we can deploy quickly, there's no sort of churn with that. We also have some libraries that we use to read this data. We've had really good luck with Zookeeper. We've really tried to break it at times. I've been really impressed by its ability to resist us trying to break it. And if you use it right, you have to make sure that you're not, you have to be very, very, once you've kind of set up the system like what we have, it works fantastic. You just have to make sure you're not overloading it. You can't, Zookeeper does not, one thing Zookeeper does not deal well with is being overloaded. So you want to keep your CPU usage very, very low on your Zookeeper ensemble. But once you have that, it works just absolutely fantastically. We will have a multi-region strategy coming. Basically, we think this is just going to be a 3-node ensemble with sort of a pair of observers in each region, but we'll see how that comes together. So you're probably actually saying, like, OK, he hasn't even talked about Cassandra like really once. So we have moved a ton of data to Cassandra from Redis. It's really about data that's too big for one machine, and that's where Cassandra really shines. This isn't data where we're going to have like hotspots where like getting like 150,000 million requests per second to like one partition of data. So we moved a couple of things. We have ad serving metadata. So yay ads, we make money. That data, we have some of that metadata is stored in Cassandra, particularly the stuff that we need when the user accesses their feed directly. We have like some extra metadata around account suggestions. So when you follow somebody, we give you some suggestions of who to follow. We have some extra metadata in Cassandra that sort of complements some other backend stuff that we have. We track churn with it, so people that are leaving this, so that haven't used the site for a while, we kind of track some of their activity. And we make sure that when people are leaving, we have some things we can do to kind of like try to, oh my God, please come back, so that we keep our numbers high. Also, follow requests. So this is more of a user-facing feature. This is basically when somebody's private and I want to follow them, I can't just follow them. They need to approve me, and all that data is stored in Cassandra. Now, some of this stuff wasn't necessarily a drop-in, and a lot of it is because, like, some of the stuff I said earlier around, like, for instance, you have to, a lot of the way that you build something in Redis, if it's like a single instance, doesn't necessarily take into consideration the fact that you might need to sort of shard this in the future. It makes some things very easy, like set intersection across keys and things like that. So we had to make some changes to our queries to support some of this stuff. So like, this is a good example of like our friend request system. You have a source, a user A wants to follow user B. So we actually will we have 2 column families to represent this instead of 1, because we need to, we have to sort of denormalize this to answer our queries. So we have, this is really simple. This is very, fairly elementary Cassandra stuff. We insert a row both in the, or a column both in the A row as well as the B row here. One for outbound requests and one for inbound requests. So we can query it, in a natural form that is really friendly to Cassandra. So, moving on. This is the big thing that we did with Cassandra this year. Actually, towards the end of last year, we built this totally new category of functionality in our product called Instagram Direct. It's a one-to-many photo and video messaging system. Basically, when you decide to share a photo directly with some people, you specify your recipients directly, and you get a little thread around these pieces of media with comments and likes and all the things that people are used to on a social product like Instagram. And the really interesting part about it is all that data is shared with all the recipients. So unlike a lot of sort of direct messaging stuff, it's more sort of group-centric. So why did we decide to use Cassandra in the first place? Well, this was a totally new group of functionality. We basically just had no way to model the type of capacity we'd need. We knew we had a lot of users, so I think at the time, official number was like 150 million users. That's a lot of people, and a lot of the time they come in and they kick the tires, and we didn't know what to expect. So the ability to scale up and then scale back down was really, really important. We were on EC2 at the time. We basically just way over-provisioned it, which made us feel really comfortable, and then we could just shrink it back down to the right size later. The write availability was also important. It wasn't like an absolute requirement, but we wanted to make this product really reliable, and this gives us a few extra sort of arrows in our quiver in terms of reliability. Just the ability to sort of, if a node goes down, we can still write to things. The storage efficiency was really good. Cassandra has compression, of course, with log-structured storage. It beats sort of B-tree style storage pretty handily. The other thing is the data model was a good fit. This sort of ordered map data model that Cassandra gives us, that a lot of people call like sort of this time series model, works as a really good fit for this sort of messaging where you have sort of a continuous sort of log of operations. We also really we also felt like the atomic batches that were added in 1.2 made a big difference in terms of the ability for us to get data out to the whole cluster and have it all sort of eventually sort of propagate properly, and we didn't have to worry about what happens if like this row gets there and this other row doesn't, and sort of all those edge cases that cause problems. We did choose Thrift. This was a difficult decision to make. We were a little bit uncomfortable at the time. This is the end of last year, so this is almost a year ago at this point. We were uncomfortable with kind of a few of the sort of issues still remaining with CQL3 at the time. We really wanted to use CQL3 with collections. That would have made a lot of this logic, this fetching logic and all these things a lot better. There were issues kind of with we were using Python, so we had some issues with the client at the time. So we decided to go the tried and true route, and I'm glad we did. It made the implementation a little more difficult, but when we the launch, I think, was the way everything sort of held together was a testament to sort of sticking with sometimes with the tried and true. If we were starting today, we would totally go with CQL3. There's no question about like how it's matured and how much sort of better in the implementation is at this point. So the data model is what I'm calling fan out on write. And the reason why we decided to go this way is because caching doesn't really work for a one-to-one or one-to-many sort of model. This is because you have very few, your ratio between consumers and producers of data is pretty much even. So when you think about how you would cache something, you would have to like read it in, and then as soon as you read it, you may have to like set a scene status. Oh, I've seen that. So you do the write, and then it has to be invalidated, and then backfilled. So you always sort of end up churning, and you end up with a sort of abysmal hit rate. So doing sort of large random access, where you need to have caching in front of it to prevent your database from falling over, isn't going to work. So we did fan out on write. And what that means is that a copy of the whole thread is in everybody's inbox. And I'll talk a little bit about how that's structured in a second. The other thing that was really useful, again, were these atomic batches. They were a key feature in our implementation. It meant that we could write out data to a whole bunch of different keys, and all of it would eventually propagate to all the nodes that it needed to. We didn't have to worry about if the coordinator fails or the node, we could just, as long as we got the whole batch up to a node, and we got a response back that said, yes, I'm going to write that, we knew that it would get out to everybody. So we didn't use a cache. So normal Instagram broadcast medium, we have to have a lot of caching. We need like a 95, 96% cache hit rate to effectively serve our traffic. That means that 4% of those reads for sort of the random amount of data that you'll have in your given home feed for a user is going to have to hit a cache. So 95% hits a cache, 5%, hopefully less, hits a backend database. So what does this look like? Basically, this is a time-ordered list of threads, and they're keyed by the recipient's user ID. So in Cassandra, they are stored by the recipient's user ID. That means when I send somebody something, I write to everybody else's key row and my own. And it's not just a summary. It's actually all the data. When I actually load this page, all the data that is in, all the comments, all the likes, all the scene states, those are all actually preloaded when I load this page. So this isn't just summary data we're sending to the client. It means that this is kind of a secret sauce. I wouldn't say it's secret sauce, but it's one of the things that we do that makes Instagram fast, is that mobile latency is very high, so we need to preload all that data. We do this when the user opens the app. We load the home feed, we load notifications, we load their profile data, and now we're actually loading this direct inbox every single time the user opens the app. So how is this stored on disk? This is the inbox. We use a composite type column name. Some of you who are in the CQL3 world will find this crazy and mystifying. But basically, this is a three-part column name. We have the first one is the post ID, so it's reverse sorted. That's a concatenation of timestamp, user ID, and some extra uniqueness data that we throw in there to make sure that we don't get conflicting post IDs. We also have a type code there. And the type code is sort of defines exactly what kind of contents that column is representing. And so you can kind of think of each of these columns as sort of this immutable log of data that we're storing that represents this post. And then we have this sort of extra ID that gets added on, this entry ID. And that used by some of the types, and that represents a unique instance of that type. So for a like or a seen state, we'll have the user's ID that liked it or saw it stored in that field. A lot of fields don't necessarily use that. So this is when we actually open the post. So what you see on the left-hand side is the view in the app. And on the right-hand side is kind of a weird brain dumpy-ish kind of output of what it actually looks like in Cassandra. So we have a post header column, and that represents sort of all the immutable traits of this post, photo video URL, recipient list, all that kind of stuff. And then after that, we have this sort of seen and likes. So when somebody likes something, we add this column in that they've liked it. If they've seen it, and actually we update the seen state every single time you look at it. So every single time you look at it, we actually update the seen state. So we kind of know when we need to send you a notification or these sort of various other things that we need to do around scene state. Most of the columns appear on all copies of the data. So like the post header, the scene, the like, any of these comments, this appears, it's broadcasted to everybody's inbox. Some of them don't. There's certain kinds of columns like hidden. Like if you mark something as hidden, that only gets written to your inbox. So there's certain things that don't necessarily need to get written everywhere. Some types of the column values are thrift serialized. So like the post header, we use thrift to serialize the data and stick it in there. Moving along. This is an immutable log. It's really easy to reason about. It avoids a lot of the concurrency pitfalls. Most of the state transitions are just moving data forward. Things go from existent to non-existent. They can't go back to existing again. The only exception to that would be likes. So you can like and unlike and like and unlike. Probably fine. The other thing we did here is we wanted to filter on read. So we calculate the visibility of whether you can see something in your inbox at read time. And what this does is it simplifies all of the state transitions. There's all these rules about when can I see something in my inbox? When can somebody send me a message? Do I follow them? Have I whitelisted them? Am I blocking them? All these kinds of things that you have to take into consideration. So we do this all at read time. And the really important thing is that this means fixing a bug means rolling out a patch. If you do things at write time, if you try to encode the logic of the application into the storage system at write time, you're stuck with it. It's very, very difficult to move things back. It's not just rolling out a patch. You got to either have some weird thing that knows about the old version and tries to work it towards where it's fixed. It's a mess. We also, to kind of get around, this sort of thrashing issue where some of the reasons why we may want you to see something or not, like whether you follow somebody or something, are conditional. It's based on whether you've read the message or not. So we use read marking to prevent sort of things appearing and disappearing and appearing in your inbox when it makes sense. So CQL3 would have made this way easier. I think again now it would have definitely been the way to go. A good example of this is if we get a page. We paginate all this data down when we send it to the client. If we get that slice out of Cassandra and it's got a partial post at the end that we need to send back, so it hasn't gotten all the data for that post, we have to do another fetch to go get that data to kind of complete it. There's a lot of crazy logic around that. So you can't send stuff to everybody, and we wanted to provide an opportunity even if these people aren't preordained. Content from your accounts that can't send to you, content from accounts that can't send to you, appear in your pending queue. And this looks like this. So when I open up my inbox, my pending queue is checked, and a little cat will appear here that tells me I have a pending request. When I open that up, I get the list of accounts that are trying to send me a message. Now, behind the scenes, these are actually post IDs, and they're all aggregated into single users. When I accept this user, they're added to my whitelist, and if I reject them, they're added to a blacklist, and that's also stored in Cassandra. What does this look like? So the post ID, actually the way this works is it's a little bit weird, is we actually add the post ID to every recipient's pending queue, even if we know they can view it or not, so we can do those read time visibility checks. And the first time a user reads that post, we just delete that column from the pending queue. It's really simple. And we do these sort of opportunistic checks to purge this pending queue so that it doesn't just grow in an unbounded fashion. The other thing we had to do is we had to, when you approve somebody out of that pending queue, we have to make sure their content appears at the top so that it's a little bit more usable. So we created this sort of pointer, and And this pointer will say, go to this other record further down in the feed. And mark it also. We also mark it as bumped so that it doesn't, you don't end up with also seeing it in the bottom. This works well. Like a lot of people are saying, well, doesn't this mean you're doing all kinds of fetching? This works well because it's not used often, and most of the time the data is already in the same page anyway. So we don't have to go very far forward to find this data. We've usually already fetched it from Cassandra. So this is Justin Bieber. He is a celebrity. Anybody that runs a sort of social site does not necessarily like this person because they fill all their databases up and break everything. And of course, with Direct, fans send him content every day. So this is something that we knew we were going to have to deal with. And he never sees any of this content. All that invisible content, because of our read-time visibility checks, get added to his inbox row. And slow is fine, but it should probably load most of the time. So what we do is we do this purge operation. So when the pending queue grows to a certain size, we trim the bottom of it. And we use a row tombstone sort of operation with a timestamp to do that. But we know what we've trimmed out. And so what we can do is we can basically just delete those columns out of the inbox because we know he'll never see it. He has no way to approve it at this point. And then we add a little exclude flag we broadcast that exclude flag out that says like, stop sending this person any more content. Stop adding new stuff. If somebody comments on something, it won't get added to their inbox. It prevents this sort of inbox bloat from happening. And of course, yes, there are a lot of tombstones here, but this is the preferred poison versus fetching a ton of data from Cassandra. We also had this other thing called the unseen jewel. We had to say, okay, this looks like an unread post count, but it's actually not. It's the unread posts since the last time you've opened the inbox. So we didn't want to make this really annoying where it would just stack up over time. You'd have this number that constantly plagues you, like everybody, I'm sure in here's inbox, has the little number that says like 5,000 on it or something. I know mine does. So this is the unread post since the last time the user opened the inbox. So when somebody taps on this, we clear it. What does this look like? It's pretty simple. We have a column family that stores basically a list of post IDs for stuff that you haven't seen yet, or we call unseen. And so when we broadcast this out to everybody, all of the different rows that represent all the recipients. And so, like for instance, if I have 8 columns in here, that's an 8. And when I tap on it, we just delete the whole row. And so it goes back to nothing. And this works really, really well. Row level deletion is very efficient. It kicks a lot of short circuit logic in. And this is actually, so this insert is actually write time visible checked, which is a little bit of an exception. But that works because that's a more sort of conservative way to go. We're not putting badging people that won't be able to see that content when they open their app. The deployment went really well. We had 60 instances we spun up just a few days before the launch on EC2. These are really big SSD instances. There's newer, better, fancier ones now. Now this is 2 times our highest estimate. So we kind of got together. We tried to think about what is the sort of worst case scenario of our user base, and we were like, okay, just double that, because we knew we could just shrink the cluster back down, and that was really important. It gave us a lot of peace of mind. And also the data models really over time, if you look back, the data models held together pretty well, I would say. We've accumulated a lot of data in here, and things have done really well. We've had millions and millions and bazillions of people exchanging messages, and things have gone pretty well. All right, so that concludes sort of the data modeling section of the talk. I want to talk just briefly about kind of a few things we learned running Cassandra in production. We had I personally had a lot of fun with Java's young garbage collection process just a couple of months back. We kept noticing that we kept piling more and more reads onto one of our busiest clusters to the point where it got to be like 20-to-1 reads to writes. That's not typical what you hear out of Cassandra. And so we saw these sort of high P99 times, so top 1 percentile latency, and it started to drag up our mean times. So this is what our mean times look like, and this is the frustrating part, is off peak, they were flat. They were less than 1 millisecond. Like Graphite can't even show you less than 1 millisecond. So it's in the sort of the microsecond I'm hundreds of microseconds category. Now, when our traffic started to ramp up, it would just surge. Now, our traffic doesn't 20x between our peak and our peak and our valley. But our latency was. It was 20, 30x. So I went through some of the garbage collection logs. We saw a lot of these sort of really expensive young garbage collection pauses that were happening. We saw our P99 times go up above 90 milliseconds for mean, actually. So all the times were getting drug up by the P99 times. All the mean times were. So in Cassandra, reads generate a ton of garbage, even if they don't read anything. Even if it's a not found, you're going to generate a bunch of garbage. We also ran into this really scary, actually, when you find bugs in the JVM, it's just not, you just want to stick your head in the sand. You hope that your whole world starts falling apart. You hope that stable platform you've built everything on is actually working. And apparently this double collection race condition sort of bug popped up and was showing up in our logs. It would run a collection, then immediately run another one. And the other one would take just as long, even though it would clear almost no data out of the heap because there was nothing in there. Again, young generation garbage collections are stop the world. So they're the kinds that cause your whole app to pause and cause Cassandra to pause. So you want to make sure these are efficient and that these are working well. And the best practices that we read were largely around nodes with way more writes than reads, or pretty much even write-to-read ratio, which we were way skewed the other direction. A best practice for this type of nodes we were using was like a 2 gig young gen and a 16 gig total heap. So we were running a 10 gig young gen and a 20 gig heap. And most people would say that's just freaking crazy to do that. But it works really well. Our P99s are down drastically. Our off-peak mean read latency is now within 2x of the on-peak. Sorry, the other way around. So when we're at peak, we're only 2 times worse than we are when we're off-peak, which is actually pretty good. And that's reduced almost 10x, which I'm very, very happy with. It didn't work out of the box. So just blowing up the heap didn't work out of the box. And I'm going to go through a bunch of really weird JVM settings that I found. I have 3 minutes, so I have to go really quickly through them. And a lot of people are saying, like, okay, young generation, now what does that do to the old generation? So we actually, without any tuning, the old generation collections become the problem. We saw these big spikes that would happen. Every minute or so, the cluster would, latency would go up like this, and go up like this, and go up like this, and it was no fun. So a lot of people are like, I thought the old gen was concurrent. Well, it is concurrent, but there are stop-the-world pauses in that old generation. So we added this. This basically means that it runs a young GC before the stop-the-world remark phase of the old generation collection, blah, blah, blah. Basically, this remark time, this stop-the-world remark time, depends on how much data you have in your young gen. So the young GC is way cheaper than one of these longer sort of remark processes. Again, remark stops the world. Very important to get that down for latency. We had to bump this. So the old gen collector does a concurrent pre-clean of the young gen data. Again, this is concurrent, so it's not stopping the world, but the problem is that if it aborts in the middle of that process because it's taking too long, it puts a bunch of extra work on this other phase of the old gen GC called the rescan phase. The default is only 5 seconds. We had to bump this way up to 60 seconds. This is in milliseconds. We saw seconds. We saw rescan pauses that took seconds. That's a huge problem. You never want your stop-the-world GC pauses to be seconds. This other one, basically the old gen will wait a bit for the young GC to occur before running this another stop-the-world phase called the initial mark. There's a timeout. The default is 2 seconds. The problem is that when we moved our heap size up really high, our young gen heap really high, during off-peak, when we had far less collections, they didn't occur within that 2-second timeout period. So it moved a bunch of work into this stop-the-world initial mark phase. Again, another stop-the-world phase. You have to be very careful about these. And this initial mark phase was scaling with the amount of data in the Eden space. So waiting for this, it's waiting for this thing to trigger, and it times out, and it's like, oh, a bunch of work on this initial mark phase because there's a bunch of data in the Eden space. These are 2 options that were actually added to the 2.0.11 and higher and 2.1.1 and higher version of Cassandra. This patch is in, it's committed. This basically makes these stop-the-world phases way more efficient. We saw basically a 5x improvement in performance when we added the CMS EDN chunks record always option. It was great. And we've got our perf up to the point where we're running on this hardware. We've moved from EC2 into Facebook data centers. We're running on 20-core Ivy Bridge hardware, 144 gigs of RAM, PCIe flash that we don't actually need, but that's what we have. We're getting 15,000 reads a second, 2,000 writes a second on this particular configuration with these heap settings. And there's a dog, but I don't have time to talk about the dog, so I have to bid you guys goodbye. Thank you very much for coming in and watching my talk. I hope you guys got something out of it. If you have any Q&A,